Welcome back to Forge College. I'm your chief engineer for today's explainer, and I gotta say, I am absolutely thrilled to share this new schematic with you. Now, in our previous lesson, mapping account primitives between Ethereum and Solana, we covered the absolute basics. Today, we're taking those raw materials and looking at the actual blueprint for navigating EVM to SVM state trade-offs. We're gonna figure out exactly how to structure your state management so your decentralized apps run fast, stay incredibly secure, and most importantly, don't break the bank.
So this brings us to a very real question you have to ask yourself as a Web3 developer. You know the parts now, right? But can you actually build the machine without it exploding or costing an absolute fortune in gas fees? Because, look, it's one thing to know what a storage slot is on paper. It is an entirely different beast to architect a high-traffic application without accidentally creating a massive bottleneck.
All right, here is our literal schematic for building scalable, secure applications today. 1. The architecture challenge. 2. Mutability and ownership. 3. Interaction and performance. 4. Real-world blueprints. 5. The decision matrix. And finally, 6. Final takeaways. Let's jump right in.
Starting off with Section 1, the architecture challenge. This is where we officially transition from the theoretical physics of blockchains to laying down some foundational concrete.
Okay, so the core divergence between these two networks really comes down to how they pack their bags. Think of Ethereum like someone who stuffs everything, executable code, persistent storage, the whole shebang, into one massive carry-on bag, the contract account. It carries all its baggage internally. Solana, on the other hand, makes you completely separate your programs from the accounts holding the data. You literally have to explicitly declare every single piece of your luggage at the check-in desk before you are allowed to fly.
Moving right along to Section 2, Mutability and Ownership. Let's examine the structural forces of our machine, specifically how your data actually changes over time and, ultimately, who holds the keys to it.
Basically, every architectural requirement relies on picking one of these three mutability patterns. First up, immutable data. You write it once, and it never changes. It's highly cache-friendly and cheap. Second, single writer mutable. This gives one central authority the power to update data right there in place. It definitely reduces coordination overhead, but you are centralizing power. And finally, append-only state. Instead of overwriting old data, you just add new records. Sure, it uses way more storage, but it preserves a perfect history, which is going to make your smart contract auditors very, very happy.
Now, the lifecycle mechanics here are drastically different. On the EVM, the contract just implicitly owns its storage. If the contract self-destructs, well, the code and the storage go down with the ship together. But on the SVM, ownership is super explicit. Because an account has a completely separate rent and balance model, you have to actively allocate and fund it. Solana operates on strict rent economics. If you don't plan for rent exemption, your account might literally get evicted by the network. No joke.
All right, stepping into Section 3, Interaction and Performance. It's time to look at the schematics for how these accounts actually talk to each other when your app is getting hammered by heavy user load.
So on Solana, everything runs on Cross-Program Invocations, or CPIs. These are essentially the internal wiring of the network. Remember how we said you have to declare your baggage up front? Well, because transactions require explicit manifests detailing exactly which accounts are going to be touched, the Solana runtime can just look at a batch of transactions and safely parallelize any that don't overlap. It is an absolute game changer for performance.
But we have to talk about concurrency hazards. Ethereum's dynamic message calls are incredibly flexible. You can build complex call chains on the fly. But that exact flexibility is what keeps auditors awake at night. It invites those dreaded reentrancy attacks where a contract is hijacked before its first execution even finishes. Solana completely avoids this by demanding strict upfront permissioning. The trade-off? Solana gives you blazing parallel speed, but you have to meticulously plan out your account list before you hit execute.
And hey, we can't talk architecture without talking about the budget. On the EVM, you're charged gas for every single opcode and storage write. Writing over and over is just going to drain your wallet. On the SVM, you're charged for compute units, plus those persistent rent costs we talked about for storage. If you wire your app wrong, like constantly writing to a centralized storage slot on the EVM or over-allocating unnecessary accounts on the SVM, you are going to burn through your operational budget faster than you can say insufficient funds.
Welcome to Section 4, Real-World Blueprints. We've looked at the individual parts and the forces at play. Now let's actually build something.
Let's apply these theories to an actual building, like a decentralized exchange or DEX. If your goal is high-throughput matching, you've got a major problem on the EVM. A centralized order book living in a single contract creates massive contention. It's like everyone trying to squeeze through the exact same door at once. The SVM solution? You shard the state. By separating orders into disjoint per-user accounts, the Solana runtime can process them all in parallel. Sharding is absolutely your secret weapon here.
But conversely, let's look at a governance contract. Here your goal isn't speed at all, it's strong invariance and single-writer safety. You're basically building a hyper-secure vault. In this scenario, Ethereum's centralized contract model actually gives you a huge advantage. Because the code and state are encapsulated together, auditing logical ownership is much simpler. The challenge on Solana is that because your code and data are separated, you have to rigorously manage owner pointers across different programs just to make sure nobody is tampering with the data.
So, what about when you're moving tokens across multiple users simultaneously? With atomic multi-account updates, the EVM naturally reverts the whole chain on failure. That's great, but it risks complex reentrancy states. The SVM, however, will execute its CPIs or fail cleanly based entirely on those upfront manifests. The real trick on Solana is to use lightweight aggregator accounts that only read or apply batched updates, preventing you from accidentally locking up your entire application.
Let's slide right into Section 5 and see how all of this builds into our favorite engineering artifact, the decision matrix.
We aren't just going to leave you hanging with abstract theory here. We are handing you a literal blueprint template. This decision matrix maps your abstract project goals directly to concrete architectural models, complete with concise rationales. It basically forces you to explicitly state your goal, commit to a model, and defend it.
This matrix right here is your ultimate cheat sheet. If your goal is high throughput, your recommended model is sharded per user accounts so the runtime can parallelize. Need single-writer safety? A central contract account simplifies those authority checks. Going for auditability, append-only event logs will preserve your history perfectly. And for low storage cost, just reuse accounts and compact your state. Seriously, lock this table in your toolkit right now so you can instantly resolve any architectural debates with your team.
And finally, we've reached Section 6, Final Takeaways. Let's quickly review the final specs before we close out today's build. Always keep these 3 core architectural principles in mind. First, always map your non-functional requirements to a specific mutability pattern. Second, treat data ownership and lifecycle as first-class design inputs. So, plan for account rent on Solana or migration proxies on Ethereum. And third, make those cross-account interactions explicit early on. If you want speed and concurrency, you absolutely must declare your dependencies up front.
To wrap things up, I want to leave you with this provocative thought. When you're faced with conflicting goals, like needing both lightning-fast, low-latency updates and strict audit trails, how will you map your decision table into concrete SVM implementation sketches? How do you actually balance those trade-offs? To learn how to turn these blueprints into actual code and dive deeper into all things Web3, make sure to visit our website at forge.college. This explainer was brought to you by Forge College, and we honestly can't wait to see what you build next. Catch you later.